Example 7.1. A, what is the voltage across the 5 ohm and the current through the 6 ohm using series and parallel reduction techniques? Finally, what is the power delivered by the 12-volt source? I will use the exact same reduction techniques for series and parallel capacitors now applied to resistors. In other words, identify all nodes and color them. If two elements have one color between them, they are in series. If two elements have two colors between them, they are in parallel. So then redraw the circuit to put it into a more manageable form. Okay, so then maybe I should say this. So then redraw the circuit to put it into a more manageable form for you that keeps track of what you want to calculate. So in this case, we're trying to calculate the voltage of the 5 ohm and the current through the 6 ohm. So you want to keep the details of those two alive. So let's go draw the circuit here. So if I draw the circuit, I'm going to say that I'm going to have something like this. So I have my source. And we know this is 12 volts. So then I'm going to go out, let's say, come out here. And then I have my first branch. I'm going to come up here with my first branch. I'm going to say that this here, I have one resistor here. And then this guy is going to go down to, let's say, all the way to here. Now, I'm actually going to lower this down. Now I have two resistors in parallel. So I have this guy and these guys are connected in parallel with one in series, and it goes like this. So then I start to, I'm going to look, let's label all the resistors with their values. And then here's my ground. So what are the things that we know? We know that this node right here has to be 12 volts. So I know this is 12 volts, and I'm going to call that node A. Then I have another node right here, which I'm going to call node B. Then I see this node right here, which I'm going to call node C. And then I have my ground. So I know that this is 0 volts, but I'm going to call this node D here. So I have 4 nodes. So what am I trying to calculate? I'm going to try to calculate this current right here. This is the current of the 6 ohm resistor. And then I want this voltage of the 5 ohm resistor. So I'm going to try to keep track of these to the best of my ability here. So now that I have that, what I want to do is that I want to show you just one small trick before we get started. So I'm going to say that this is a useful identity. So if I have a resistor, let's call this as R12. These two resistors are in parallel. If you do the algebra, we can write this as this combination. So two resistors in parallel is you multiply the products divided by the sum of them. This is very, very handy. And I will use this almost immediately. So I'm looking at the circuit here. And so now what I'm going to do here is use resistor reduction to simplify the circuit while tracking the changes for the 6 ohm and 5 ohm resistors. So the first thing I'm going to look at is I'm going to follow the same process that we talked about. So I'm going to look for what's in parallel first. What are two resistors that have two colors connected to them? And you could see here is that I have resistors 6 and 12 between A and B, and those guys are in parallel. So I'm going to rewrite that. So let's do that. So the first thing I'll do is I'm going to say that between A and B nodes, the 6 ohm and 12 ohm are in parallel. So I typically don't do that. The way I write this is that I just say, I say that 6 is parallel to 12. Okay, so if they're in parallel, then I'm going to calculate the resistance. So now calculate this equivalent resistance. So the way we typically do it is we then go AB is then going to be 1 over 6 plus 1 over 12. But if you use that identity that I talked about, then this is the resistance of AB. So then I take both resistors and I add them in the denominator. Now I multiply them. And when you do that, you get a 4 ohm resistor. And so this is what I would say is 6 parallel to 12, which is the resistance AB. So now I have that resistor. Now, how do I track this thing here? We want the current of the 6 ohm resistor. Okay. To calculate I6 ohm, note that parallel resistors have the same voltages. So in other words, the voltage of the equivalent resistance, which is 4, is also the voltage across the 6 ohm, which is also the voltage across the 12 ohm. So whatever we calculate, so if I want the current, then the current of the 6 ohm will then be the voltage of the 4 ohm divided by 6 ohm. So then what we're seeing here is that our job here is that we want to solve for delta V4. So if we do that, we can calculate the current, which is what we want. So the next thing that I want to do is redraw the circuit. So now I'm going to redraw the equivalent reduced circuit. So this is my circuit here. So if I look at this circuit, the way I'm going to redraw this here is that I'm going to draw this as one resistor. So then that means I'm going to come over here and I'll say that here's my here's my source. So then if I look at my resistor here, I'm going to say this is this resistor. And then I have a second resistor, or second branch, I should say. And so this guy now is my 4 ohm. This is still my 4 ohm. This is my 3 ohm, and this is my 5 ohm. And so what I'm seeing here is that now we want to calculate that guy, and we want to calculate this one right here. So if I set this up, we then go in our draw our nodes again. So our nodes here is then going to be They're the exact as before, but now it's simplified. And so, again, this is node A, B, C, D, where of course this is ground and this is 12 volts. So once again, we contain that current within that. So if I focus, just rewrite this one more time, I see that when I look at that 4 ohm, what do I actually have? I know that this guy here is my 4 volts here. And this is, but this is really this guy. So in this situation, we see that this guy has to be our 6 ohm. This has to be our 12 ohm. And this is our current of the 6 ohm that we're trying to calculate. So now let's calculate these guys. So we want to calculate the current I of the 6 ohm and voltage delta V 5 ohm. There are numerous ways to calculate these quantities. However, I will only show one way to do this. Which is most efficient. Note, this circuit is mainly parallel in nature, which allows us to make this observation. So when you look at that circuit, I'm really seeing something like this. I essentially have a block right here, and I have another block right here. So if I'm looking at these quantities, I'm seeing something like this. Now, the fact that I said that this was more parallel than series is because of this fact. So if I take those two resistors and I block them out as I just did here, then you can clearly see that there are two. There are two nodes only. So what this is really telling us here is that these are in parallel, and that just means same voltages that allows us to break apart into an easier form. So what I'm saying here is that if this is 12 volts here, and this guy is 0 volts, then that means here that the voltages across the blue and the green must be 12 volts. They essentially form an independent loop, but there's a problem here. The source current coming here is not the same through the green or the blue branches. So you gotta pay attention to that. So the only way this makes sense here is if we don't try to calculate the current around the loop. So then what I see here is that there's an upper and there's a lower branch. So if I look at the lower branch, what do I see? I see a circuit that looks like this. I have a circuit that looks like this. And this is then going to equal this guy. So in other words, if I distribute these guys, then this guy here is then going to be my 3 ohm. This is my 5 ohm. And of course, this is my source. And we're after this guy. Versus the upper branch. You know what? This is the exact same circuit, so I'm going to just copy it and modify it. So if I copy this guy, then I have this thing right here. But now this is not green, and these resistor values are not the same values, but this is now blue, and we then have that this is a 4 ohm, this is a 4 ohm, and that what we're interested is in calculating this voltage right here. Oops, no, wrong place. It's over here. I mean, by drawing it this way, so doing this dramatically reduces the complexity of the circuit. So staying away from currents, we can use VDR to calculate these voltages. So if I look at the first branch, let's think about the lower branch. The lower branch then says this. So for this lower one, here we want to calculate the voltage delta V 5 ohm. So if I look at this circuit, I'm going to have this. So here's my circuit right here. So VDR then says this. So then VDR then says that the voltage across the 5 ohm has to be the sum of the resistors, which is 3.3 plus 5, and then it has to be the actual resistor times 12 volts. So if I calculate this number, I get 7.5 volts. And this is the voltage of the 5 ohm resistor. Now, if I go to the upper branch, I'm going to get this guy. Doing the upper branch now. We want to calculate delta V 4 ohm and current through the 6 ohm. I then put in my circuit. So I'm going to use VDR. So then VDR tells me here is that the voltage of the 4 ohm is going to be 4 plus 4 divided into 4 times 12 volts. And this will give me 6 volts for V 4 ohm. But now, if I use Ohm's law, I now can calculate the current I6 ohms. Which would then be 6 over 6, which gives me 1 amp for that current. So now we've calculated our quantities without too much work here. Now let's go to B. So in B here, we want to calculate the power delivered by the 12-volt source. And that means that if I have a source, I must use the voltage times the current. That is the definition. Now note that for resistors and capacitors, we could modify that, but we know what the voltage is. So what this is telling us here is that the goal now is to calculate the current of the source, which is I of 12 volts. There are two ways to calculate the source current I 12 volts. One of the most common ways that people do is that they determine the equivalent resistance and apply Ohm's law. Or we can use existing values to determine I 12 volts. So let's do the equivalent resistance circuit first. So this will be the equivalent resistance method. So we start with the circuit. And reduce it to a single equivalent resistance. So I have the image from up above, which looks like this. Here's my circuit right here. So now I'm going to reduce this now. If I reduce this, by the way, this is not 5, this is a 4. Okay. So when I look at this thing, you can see that I have two resistors in parallel plus 2 in series in each of the branches. So when I'm looking at this guy, here's what I have. I'm going to see that the first branch then tells me that I can replace this circuit with the single resistor that reads as 4 plus 4, which will give me 8 ohms. And then this guy is going to give me another resistor with 3 plus 5, which is 8 ohms. And then I have my source right here. Now I can apply our parallel one and then say that these two are in parallel. So if these two are in parallel, since there's only two nodes, this should be 8 plus 8 in the denominator, 8 times 8 in the numerator, and that gives me 4.0 ohms. So that means here that now I have a single resistor in my circuit. And this tells me that this is now R equivalent is equal to 4 ohms. And our goal here is to calculate what the current is of the 12-volt source. So I want to calculate the current. I 12 volts using Ohm's law and the power of the 12-volt source. So then Ohm's law tells us this. Says that the current of the 12-volt source is going to be the voltage of the 12-volt source divided by R equivalent, which then will be 12 divided by 4, which then gives me 3.0 amps for the 12-volt source. But the power shows that the power of the 12-volt, now because this is an active source, I put in by hand a negative sign. This should be the voltage of the 12-volt source times the current of the 12-volt source. So then that means this is going to be minus 12 volts times 3 amps. So I'm going to get minus 36 watts. And that's going to be the power of the 12-volt source. So now I have the power. Now, the second method here is using values already calculated. So if I look at my circuit, it looks something like this. We have the following circuit with the calculated values. So if I come in here and I put my circuit back in, we calculated what the voltage was of this guy right here. We calculated the voltage of this guy right here. We should use them. And so what you're seeing here is that when I look at the current, we see here is that there's a current of the 12 volt. And then we're going to say that we're then going to have a current coming down here. And I'm going to say that this is the current of the lower branch. And then I have a current coming in here, which will be the current of the upper branch. And according to KCL, we're seeing here that the current of the 12-volt source must be the current of the lower branch plus the current of the upper branch. But we know what those voltages are, and therefore we know what the current is. So if I look at the current of lower branch, resistors 3 and 5 ohm are in series. So that means here that the voltage of the 5 ohm must be the same as 5 ohm times the current of the lower branch. So then that tells us that now we can solve for that current because we know the resistance and we know the voltage. So therefore, this tells me that the current of the 5 ohm is then going to be, what's the voltage of the 5 ohm? I don't remember what it is. I have to go find it. We calculated at 7.5. So this guy is then 7.5 divided into 5 ohms. I'm going to get a value of 3/2 amps. So in other words, I know what the current is, and this current here is that of the lower branch. So now if I repeat the exact same thing for the upper branch, then I'm going to see this. So now the current of upper branch between the 4, look at that, I put a 5 in here again. That should be a 4. The 4 ohm and 4 ohm resistors are in series. So that means here that they're going to have the same current. So then the voltage of the 4 ohm is then going to be 4 times the current of the upper branch. And this should then be the voltage of the 4 volt. I believe, wait, that tells us here that this should have the current of the upper is then going to be the voltage of the 4 ohm divided by 4 ohms. And that also turns out to be 3/2 amps, which is also, again, the 4 ohm current. So now we can put this all together and then say the current of the 12-volt source is then going to be I of 12 volts. It's going to be the current of the 4 ohm plus the current of the 5 ohm. And we see that we're going to get 3/2 plus 3/2, which then gives me 3 amps. And that's the current of the 12-volt source.